Hello guys. Welcome to my channel YouTube. This video introduces arrangement and explains how to evaluate arrangement, as well as solve counting problems using arrangement. Before watching this video, please like and subscribe. Okay guys. Are arrangements by n are arrangement of n distinct objects. We mean an ordered selection of r of the objects. We use the symbol p, n, r to represent the number of r arrangements of distinct objects. The 6 3 arrangements of the distinct symbols a, b, and c are a, b, c, bag, g, cab, b. Theorem I let p, n, r be the number of r arrangements of n distinct objects, then p, n, r equals n minus 1, n minus 2. n minus r plus 1 equals n rank r. Proof 1. Consider r labeled boxes to be filled, each with one object selected from the n distinct objects. There are n choices for the first box, n minus 1 for the second, and r plus 1 for the rth. 2. There are p, n, r1 ordered arrangements of n distinct objects taken r1 at a time. For each such arrangement, there will be n r plus 1 remaining objects. Again, applying the multiplication principle, we may state that the total number of r arrangements of n distinct objects is n r plus 1, p, n, r1. Thus, p, n, r equals n r plus I, p, n, r1. By analogy, p, n, r minus 1, n r plus 2, p, n, r minus 2, p, n, r2, n r plus 3, p, n, r3, p, n, 3 equals n2, p, n, 2, p, n, 2 equals n minus 1, p, n, 1, p, n, 1 equals n. Now multiply corresponding members of these equations and cancel the common factors to obtain p, n, r equals n r plus 1, n r plus 2, n minus 2, n minus 1, n equals n rank r. As required. Theorem 2. The number of arrangements of n distinct objects taken r at a time with unlimited repetitions allowed is. The reader may prove Theorem 2 using the multiplication principle. In such a case, only the relative position of the objects is of interest. We consider only the relative position of the objects A, B, C, and D, and not the positions themselves. Theorem 3. The number of ordered arrangements of n objects in a circle. The theorem may be proved by observing that we may arbitrarily seat one person at a round table, and we then have n1 choices for the person to the right of him. Theorem 4. The number of n arrangements of n objects of which exactly p are alike of one kind and exactly q are alike of a second kind, with the remainder all different, is n/p q. Example: consider the collection A equals A, B, B, in which we consider the 3 A's and 2 B's to be 5 distinct objects. Here n equals 5, p equals 3, and q 2. According to the formula in Theorem 4, the number of ordered arrangements of all of these objects is 5 divided by 3. 2 equals 10. Proof of theorem: let x be the required number of arrangements. Let the n objects be labeled x1, x2, xn, with the p alike of one kind labeled x1, x2, xp, and the q alike of the second kind labeled xp plus 1, xp plus q. Then there will be n arrangements of these now distinct labeled objects, and so n xp q. Since for each of the x required arrangements, the first p alike, being labeled, can be interchanged in p ways, and the q alike of a second kind, being labeled, can be interchanged in q ways. Thus the theorem is proved. Finally, Theorem 5 deals with the number of ways of making selections from a given set of objects. Theorem 5. The number of ways of making a non-empty selection by choosing some or all of P1 plus P2 plus part objects where P1 are alike of one kind, P2 alike of a second kind, part alike of a kth kind, is P1 plus 1, P2 plus 2, part plus 1 dash 1. Proof: the P-like objects yield pi plus 1 selections for each I, since we can choose either 0, 1, 2, or pi objects from that subset. Applying the multiplication principle yields the product P1 plus 1, P2 plus 2, part plus 1, from which one selection must be subtracted to ensure that we have at least one element in cache of our selections. That is, we must exclude the possibility of taking no element from each of the k subsets.